All right, hi guys. So this is the last video, 6.1. Okay, and this is a super important video. Covers super important topics. Specifically, regions, areas of regions between two curves. Okay, so let's just recap what we know. So I have, maybe a function here. Right? And then, my integral, because this function is above the x-axis, my integral is just the area. It's just the area, right? So my integral f of x, and then let's call this a to b, call this f of x, right? A to b, f of x dx. This is just the area under the curve, f of x, okay? Notice here, though, it's only one curve and the x-axis. Now, technically, the x-axis is a function. It's just y equals 0, right? It's just 0. Um, we'll talk about that in a second. What if I actually have two, normal like functions, weird functions or whatever, and I want to find the area between them? So maybe something like this. So maybe call it a red function on top and maybe a blue function on the bottom. And I want to find the area between these two. Okay, so this is my A, this is my B. How do I find this area? Hmm. Well, we can do it, we can prove it with like the limit of the Riemann sum, blah, blah, blah. Um, but I want to think of it a different way. Okay, so this area here, notice it's close to the picture we drew above, right? So what I want you to notice is this is the area under the red function. Let me see if I can draw this accurately. All right, so here's A, here's B. Okay, so I just kind of took away the blue function. So notice it's this area minus the area under the blue function. Right, so here's A, here's B. Okay, hopefully you guys can see that, right? It's It's the area under the red function minus the area under the blue function. Okay, now why do I care about that? Well, in both of these two scenarios, the red and blue function, that's just one function, and I can find that area. So this is the area, maybe we'll call this red function f of x, and we'll call this blue function g of x. So this is the area, right, under f of x minus area under g of x. Right? If you have a hole there, you kind of subtracted away something, right? Maybe, hopefully that makes sense. Okay. So again, this is f of x here. This is g of x here. Okay. So this area under f of x and above g of x, right? The area between the two. This is really just the integral a to b and then f of x minus g of x, right? I can combine those two integrals into f of x minus g of x. All right, yeah, so this is our formula that we're going to be using. The area between curves, okay? So it's the top curve. It's the top curve minus the bottom curve. And then the interval is, the interval a to b or whatever that you're looking at. Okay, so let's try it. Let's try it. Okay, here we go. Let's do it. Find the area above f of x equals x plus 4 and below, excuse me, I made a slight error here. Okay, slight error. Find the area of the region, we'll call it R, which is bound above. by f of x equals x plus 4 and bound below by g of x equals 3 minus x over 2 on the interval 1 to 4. Okay, so how are we going to do this? Well, I know my area is going to be, my bounds are 1 to 4. Then which one is my top function? Okay. Well, my region is bound, it's bound above, right? It's capped or like stopped by the function above. So that's gonna be x plus 4. Okay. Now we need parentheses here. Okay, and then our bottom function, right? Process of elimination is the other one. Make sure you do parentheses. Make sure you do parentheses. Make sure you do parentheses. Okay. You do parentheses around the functions. Okay. The reason is this minus here. If you don't distribute the minus, you will get the wrong answer. Okay. So one of the key things to notice to distribute the minus is parentheses. Okay. So we're going to distribute this guy here. So this is the integral 1 to 4 and x plus 4, nothing changes there, but then it's minus 3 plus x over 2, x. Okay. So, and again, let's go 1 to 4, x plus x over 2, that's 3 halves times x, and then plus 1. And now we can do the antiderivative. So my bounds are 1 to 4. So 3 halves. Well, if I got the 3 halves, and then the antiderivative of x is going to be x 1 half x squared, excuse me. So those are multiplied. And then plus 1, antiderivative, that's x. Okay. So now let's plug in 4. So I have 3 quarters, right? The 2's combined to be a 4 there. And then 4 squared plus 4 minus 3 quarters, 1 squared plus 1. All right. So then what is this? So this is 12 plus 4. Distribute the minus sign here as well. So minus 3 quarters minus 1. Okay. So this is 15 minus 3 quarters. I just combined all the whole numbers there. So this is 14 and a quarter, which is 43 over 4. And that's the area between the two functions. Okay. So the setup takes a little bit longer. Oh, excuse me. Um, Looks like I made a mistake. Yeah, sorry. Miscalculation. 57. Okay. Um, yeah. I was thinking of something else. Whoops. All right. So, yeah, so most of it's the same, right? It's just, antiderivative, plug in the balance, blah, blah, blah. It's the setup that takes it's just an extra step, right? You do top function minus bottom function. Okay. So let me get you guys to try this one. So let's do another example here. So let's call the region R is bound above by y equals x over 2 plus 5, and it's bound below by y equals x plus a half, and then let's do on the interval 1 to 5. Okay, so now you uh, do this problem, and you can pause here that you have everything on the board. Okay, so let's go a little quicker here. So our integral, so our area is going to equal, well, the bounds are 1 to 5, that's easy. But then I have, it's bound above by x over 2 plus 5 and below by x plus a half. So gotta do parentheses, gotta do parentheses. So integral 1 to 5, this is a half x plus 5. I like writing it like that instead of x over 2. And then minus x minus a half. Okay. So what is this? A half x minus x is negative a half x. And then 5 minus a half is 4 and a half, or 9 halves. Then we can do our antiderivative. So I have a negative half times, and then the antiderivative of x. So x, add 1 to the exponent, divide by that exponent, plus, and then 9 halves x. Okay, bounds. So I have negative a quarter, and then times 5 squared, plus 9 over 2 times 5, minus negative a quarter times 1 squared plus 9 over 2 times 1. Okay, so this is negative 25 over 4 plus 45 over 2. Distribute the minus here. So that's plus a quarter minus 9 halves. Okay. And then once you add all this stuff together, you should get 12. Alrighty, let's keep going here. Okay, so we're going to switch gears here a little bit and make it slightly more complicated, just an extra step, or maybe two steps. We can combine it into one step. So far, we've had a top function and a bottom function very clearly lined out, right? What if we don't know which one's on top, or what if they switch in the middle of our interval? Okay, so the way we are going to approach this, so we're gonna, let me write it how it'll say. So find the area between f of x equals maybe sine x and g of x equals cosine x on the interval 0 to pi. Okay, notice here I said between. I don't know which one's on top, which one's on bottom. Okay, now you could graph and figure it out. Um, but sometimes functions are a little harder to graph. So here's how we're going to do it. First of all, I know my two, like my starting point and my end point, 0 and pi, but what if they intersect? Okay, so kind of conceptually, like if we take a side step here, if I have two functions, so what if one function goes like that and one function goes like that? And I want my area on this interval. So notice here, my area, my top function and bottom function switch. Okay, so what I would need to do is I would need to find this intersection point. So this is A, this is B. Maybe call it C, right? So my area will equal, let's call the top function f of x and the red function, the blue one, excuse me, f of x and the red one, g of x. So my area will be A to C of f of x minus g of x, right? Top minus bottom. I'm looking on this left interval. Then plus, if you look on the right interval, it'll be c to b, but now g of x is on top, minus f of x dx. Okay. So when you're doing area, it's always top minus bottom. Okay. So you have to look and see if there are any points where it switches, right? So, and you have to do an area for every single, region there where you do top minus bottom. Okay. Top minus bottom, top minus bottom. So for us, I need to figure out my intersection points, if there are any. So I need to set my two functions equal to each other, right? So an intersection point, they have the same y value, right? They have the same y value, and we're trying to find this x value, c. So if the y values are the same, right, you just set the two y values equal to each other. Okay, how are we going to find this, right? Sine x equals cosine x. This one's a little tougher, but we can do it. So what we can do is actually either think conceptually, right? What angle gives you the sine and cosine are the same, right? And we did it earlier in last video, excuse me. Um, yeah, so that's going to be root 2 over 2, right? They're both going to be root 2 over 2. So that angle would be pi over 4. Okay. Now, maybe you don't know your unit circle that well. You could divide cosine to the other side, and then you'll have tangent x equals 1. Maybe that helps. That would give you x equals pi over 4. Um, but yeah, so either way, we'll have to know our unit circle somehow, but that gives us pi over 4. What that means is my area is not simply 0 to pi. I'm going to have two integrals, 0 to pi over 4 of something plus another integral pi over 4 to pi of another something. Okay. But still, I don't know which one functions on top, right? Which function's on top? Well, the way we're going to do it is similar to like, what do you call it? first derivative test where we plug in points. We're going to plug in a point in each interval, right? So here, um, maybe try x equals pi over 6. That's a nice one. And then here we'll try x equals pi over 2. That's a nice one. And we're just going to plug into both functions. So we'll have sine of pi over 6. What is that? And cosine pi over 6. What is that? Okay, sine of pi over 6 is a half. Cosine is root 3 over 2. Okay, so notice there the cosine function is bigger, right? G of x. So this is f, this is g. So we're going to do g minus f, right? The bigger function minus the smaller function, right? Top minus bottom. So I'm going to have cosine x minus sine x. Then for this guy, we'll plug in again. So sine of pi over 2, cosine of pi over 2, right? So this is f, this is g, and that equals 1, that equals 0. So sine's on top now. So we're going to do sine x minus cosine x, right? We're looking for the bigger value minus the smaller value. Okay, awesome. So let's evaluate this now. This is our area. So antiderivatives here. Antiderivative of cosine is sine. Antiderivative of minus sine is plus cosine x. Okay, we have this plus, and then antiderivative of sine, negative cosine x. Antiderivative of negative cosine is negative sine x. Excuse me, pi over 4. Okay, and I will plug in. So since we have two integrals happening here, I'm going to have two big sets of brackets. And then we'll have, let's see, sine of pi over 4 plus cosine of pi over 4 minus sine of 0 plus cosine of 0. And then here we'll have minus cosine of pi minus sine of pi minus cosine of pi over 4 minus sine. Let me give myself a little more space here. Minus sine of pi over 4. Okay, a lot of negatives happening, so let's be careful here. So sine of pi over 4, that's root 2 over 2. Cosine pi over 4 is root 2 over 2 as well. Sine of 0 is 0. Cosine of 0 is 1. And then let's see, minus cosine of pi. Well, cosine of pi is negative 1. So negative cosine of pi is positive 1. That's 0. Then cosine of pi over 4 is root 2 over 2. So this is minus root 2 over 2. And this is also minus root 2 over 2. Okay. So I have root 2 over 2 plus root 2 over 2 is 2 times root 2 over 2 minus 1. And then I have a 1 plus 0 minus root 2 over 2 minus root 2 over 2. That's minus 2 times root 2 over 2. Okay, so this is root 2 minus 1 plus 1 plus root 2, right? So those two negatives cancel. Okay, so then my ones cancel and I get 2 root 2. And that's going to be the area of this region, 2 root 2. Okay. So the antiderivative parts, this is all, we've been doing this. Now here it's two of them are happening at the same time, right? But it's just more of the same, right? Be careful with your algebra, things like that. The main idea is we found our intersection points. So we split our integral up into multiple integrals. And then we figured out which function was on top and which one's on bottom by plugging in a value inside those intervals. Okay. Let me get you guys to try this one. So, so the area between f of x equals sine x and g of x equals cosine x. 1 second. Okay. And let's do it on the interval pi over 2 to 2 pi. Okay. So you guys go ahead and try this one. Pause here. Let me put everything on the board just in case you want it. So there we go. Go ahead and pause here. Okay. So let's do it. So first, let's find intersection points. So sine x equals cosine x. Um, now, sine x equals cosine x. For this interval, remember earlier we had pi over 4? Pi over 4 is not inside this interval. Okay? But there is another spot where sine x equals cosine x, and that's when they're both negative root 2 over 2. Right, so that it is 5 pi over 4, and that is in our interval. Okay? So that's why I didn't talk about 5 pi over 4 last time, because it was outside of our interval. But now that we have that, we have our two intervals. So pi over 2 to 5 pi over 4, and then 5 pi over 4 to 2 pi. And let's plug in a value in each one. So what's the value in here? So let's try x equals pi. That's in there. And then here, what's the value in here? X equals maybe 3 pi over 2. Okay, and we'll plug in. So f, so sine of pi, and then g would be cosine of pi. So sine of pi is 0, cosine of pi is negative 1. So actually sine is on top. Interesting. Then here, so f would be, so sine of 3 pi over 2, that's negative 1. And g, cosine of 3 pi over 2, that's 0. So now cosine is on top. Okay. So then our area is going to equal the integral pi over 2 to 5 pi over 4. Um, and then sine was on top. So it's sine x minus cosine x dx plus then 5 pi over 4 to 2 pi. And now cosine is on top. So cosine x minus sine x dx. Okay, so this is our setup. Hopefully you guys got here. And then I'm just going to pause here and do the rest of it. It's all very similar to the last problem now that we got the two integrals set up. Okay, and there's our solution to root 2 plus 2. Okay. All right. Let's do a slightly different example where we are given, we want to find, let's call it example here. Not necessarily area between two functions, but just a region bound by multiple functions. So find the area of the region bound by f of x equals x squared, g of x equals 2 minus x, and the x-axis. Okay. So what we need to do is figure out what the hell kind of region this is, and then we can set up our integral. Okay, probably multiple integrals, but we'll see. So, x squared, these are all functions we can graph pretty easily, actually. So x squared is going to look like that. Okay. And then 2 minus x, so maybe let's call this 1. Yeah, that makes sense. That's 1 there. That's about the same. And then 2. So 2 minus x, it's got a slope of negative 1. So it goes down like this. So then it hits at 2 there. And of course, this keeps going. But we have our region actually already. So it's the region bound by x squared, 2 minus x, and the x-axis, okay? So you always need to be looking for the region that is bound by every single one of the functions, okay? So this is the only region where all of the sides of it is one of the functions we talked about, okay? So like for example, notice this region here, this pizza slice. That does have 2 minus x as a side and x squared as a side, but it has the y-axis as the other side, not the x-axis, okay? So you just want to be super careful. It's the only region bound by all the functions specified. Now that we have this, we need to look for top and bottom functions. Okay, so what I would recommend doing is at least visualizing, but you can draw rectangles if you want, or lines. So we're starting over here. right? That's our first intersection point. And then I'm just draw some lines here. So notice for all of these lines, the top function is x squared. The bottom function is the x-axis, okay? For all these lines. Then I hit this intersection point, and then I switch my one of my functions switch, okay? Anytime either of your functions switch, that's a new integral, okay? So this integral on the left in black, that's going to be an integral. And then over here, since my top function switched, and this goes all the way till my final intersection point, that's a new integral as well. So this is our 2 minus x and our x-axis. Okay. Okay, so then what's this intersection point here? Okay, well, you set your two functions equal to each other that define the point. So what two functions are going through that point? Well, it's the x squared function, and then it's the 2 minus x. Okay, so we're just going to set those two functions equal to each other. X squared equals 2 minus x. So we can move the two things to the other side. X squared plus x minus 2 equals 0. And then we can factor. So we'll have x minus 1, x plus 2. Okay, so x equals 1 and negative 2. Now, x equals 1 is going to be our answer we care about. Negative 2 is not inside our interval, right? Notice our picture here is on the right-hand side. Negative 2 is all the way over here, right? And you can see they were going to intersect at another point, but that's not the picture we care about. We care about right here. So this is x equals 1. Okay. Now we have everything we need. So the black integral will be 0 to 1, and then top minus bottom. So x squared is the top function, and then y equals 0 is the bottom function, right? The x-axis, y equals 0. Then we have the integral 1 to 2, and then it's 2 minus x, again, minus 0, dx. Okay. Now I put the zeros there just so you could see it, but in reality we didn't need them for this example. But in other examples you might need it, okay? So I just wanted you guys to have it. Now we can do our antiderivatives. So this will be 1/3 x cubed, 0 to 1. And then this will be 2x minus a half x squared, 1 to 2. So plugging in, the zero bound gives me nothing, so this will be just a third plus, now these bounds matter, so I'll have 2 times 2 minus a half times 2 squared minus 2 times 1 minus a half times 1 squared. Okay, so this is a third plus 4 minus 2 again plus a half. Okay. So this is a third plus a half, which is 5/6. So that's the area of our region. Alrighty. So let me get you guys to try another one. Area bound by y. Let me just do f of x actually. F of x equals root x. G of x equals 3 halves minus a half x. And the x-axis. Okay, so go ahead and pause here. I'll, put this back on the board so you can really see everything happening. Pause here, draw the picture, find your top and bottom functions, find your intersection points, set up your integrals, and then evaluate your integrals. Okay. All right. I'm gonna jump to the solution here. All right, so I've got the full solution here. So I drew the pictures and they intersect at x equals 1. You could get that pretty easily from the picture if you draw it well enough, but if you set the functions equal to each other and solve, you'll get it as well. And then we did the two integrals. The first integral is nice because the lower bound is 0, so we just get 2/3. The other one, right? We plug in bounds, do the all the algebra, blah blah blah. Plug in your calculator, all that stuff. Okay. Now, we're gonna we'll shift gears here. And but before we shift gears, I want to reframe what we've learned so that it carries over to the next section a little easier. Okay. So what we've been doing is the integral a to b and then essentially the top minus bottom, right? For the area between the two functions. What I want you guys to think of it as is this is really like our bigger or more positive function, right? If it's above in our plane, right? Um, it's bigger, it's on top, but it's more positive. But instead of thinking on top, right, think bigger or more positive. Then bottom is, smaller, less positive, whatever. Okay, so that'll help us thinking of it like that. That'll help us with integrals with respect to y. Okay. What we're doing here is we have integrals now, but they're functions of y. X equals a function of y instead of y equals a function of x. Okay. So then if I want to do my integral, it's not a to b. Well, we usually use c to d on the y-axis, and we want the area in between here. Now, if we're going to do the area, so we can't do top minus bottom because we are only dealing with left to right functions. That's why I reframed it. You want to think of the bigger function or more positive. So over here, this function is more positive, right? It's further along in the x-axis. It's more to the right. And then the blue function's more to the left. It's smaller. It's smaller. So, right, you might think of this as like x equals 5 and x equals 2 or something. Obviously, functions are more complicated than that, but that's why I wanted to reframe it. So now when we have this integral, this area is from c to d, right? Small to big y values, right? And then we'll call this function f of x, not f of x, excuse me. Um, we'll call this x equals f of y, and then we'll call this x equals g of y, right? Instead of y equals f of x. And then this is f of y minus g of y, okay? So whether you want to think of it like the bigger function minus the smaller or whatever, or you could just think right minus left and top minus bottom for x, however you want to think about it, this is what we have, okay? So this is like right minus left. Okay, so this is actually how we do it. So this is kind of the setup, but what you'll find is most of this is really still the same. It's really all still the same. But the point of learning it is sometimes it makes your work a lot easier. So let's look at that first example we did. Not first, um, but like the region bound by blah, blah, blah. So we had, what was the example? So it was like f of x equals x squared, g of x equals 2 minus x, and the x-axis, right? You guys remember um, this example right here? So let's just draw the picture again really quick. So x squared, and then 2 minus x was like that. So 1, 2, 2 minus x, x squared, right? That was our region. And we split it into two integrals. Yeah, so with what we had, that was the best we could do. But now that we know how to do this, where you look right to left, this would be a lot easier actually. Okay, so if you look left, top to bottom, right, you'll see, okay, my one of my functions switched, so I have to do two integrals, right? Exactly what we just did. So then you could look, well, maybe what if I do with respect to y, which means we look at vertical, not vertical, horizontal lines. And what you notice is in the entire region, it's always the same right and left function, which means just one integral. Just like with respect to x, if you have just one top and bottom function, that's just one integral, right? You do top minus bottom. Here we do right minus left. Now the problem is these functions are not with respect to y. The variable is x. So we have y equals x squared and we have y equals 2 minus x. So for both of these, we need to solve for x. Okay, so here we can square root, and then we're only going to use the positive one because this function is on the positive side. Okay, and then here we can subtract 2 and then divide, and we get 2 minus y equals x. Now these are our two functions in terms of y. Okay, they're in terms of y. So then what this is really saying is this is root y. This is not 2 minus x, it's 2 minus y. Now we can do right minus left. Okay. But also we need y bounds. We need y bounds. So y equals 0 is the x-axis. That's our lower bound. And then this is our upper bound here. What is that y value? I know the x value is 1, right? I know the x value is 1. So we'll just plug in 1 to either of the functions and we get the y value is in fact also 1. Okay? So now we're integrating 0 to 1 and then it's right minus left. So it's 2 minus y minus root y dy. Okay? If it helps turning your head right 90 degrees, um, kind of visualizing it how we used to with respect to x. Okay, but this is what we get. So we get right minus left, and then these are y bounds. Okay, these are y bounds. So you just got to reframe everything in terms of y. It's not a substitution. You're just rearranging things around, right? You're not introducing a new variable. Y was always there. We just kind of didn't use it. But now that we have this, first of all, it's just one integral. Okay, so it's going to be less work. Is it going to be easier? Yeah, probably less algebra, right? Less options to make mistakes, less, you know, less possibility of making a, algebra mistake, right? Adding something wrong, distributing a minus wrong, whatever. Okay. But now we can just do this. So 2 minus y, that's going to be 2y minus a half y squared for the antiderivative. And this is y to the half. So it'll be minus 2/3 y to the 3/2. And then we plug in our bounds. So the zero bound will be 0. So we just plug in 1. So I get 2 minus a half minus 2/3. And that'll be I don't know what that will be. Well, it should be the same answer, but that we got because it's the same area. 5/6. Let me see if that's right. Yep, that's right. Okay. And that is the answer we got last time, right? And it better be the same answer because it's the area didn't change, right? It's the same area. Okay. It also helps us with the other example we did. So this guy right here. Again, we don't need two integrals anymore. If you look at the horizontal lines, the right and left function is always the same. So it'd actually be better to do this with respect to y. Okay, so just again, we had f of x equals root x, g of x equals 3/2 minus a half x, and then the x-axis. And then, draw the picture, right? So it looked like this and like this. Okay, so this was at 1, this was at 3, and then this is square root x, y equals square root x, and then this was y equals 3/2 minus a half x. Okay. But yeah, again, if you look at it with respect to x, you have to do two integrals, right? Because one of the functions change. If you look with respect to y, the right and left functions do not change, which means we will only have one integral. Right. This is kind of a little tip now that we're have this option of viewing it two different ways. Every time one of your functions change, whether you're doing top and bottom or right and left, every time one of those changes, that's another integral. Okay. So if one of them changes once, that's another integral, so two in total, right? If they change multiple times, that's another one and another one and another one, right? So it keeps adding up like that. Um, yeah, so let's do this with respect to y. Now, we have to reframe our functions with respect to y, which means we have to solve for x. So for this first one, x equals y squared, that's easy. We just square both sides. This one, let's see, we'll have y minus 3 halves equals negative a half x. And we multiply both sides by negative 2. We get negative 2y plus 3 equals x. Okay, and then we need our y bounds. So this is y equals 0, right? The y coordinate of this is 0. What's the y coordinate of that? Well, I don't know, but I know the x coordinate is 1. I just plug into either of my functions, and I get y equals 1 as well again. Okay, 1 as well. So now my area is going to be integral 0 to 1, and then right function, which is negative 2y plus 3 minus my left function, which is y squared dy. Okay. Again, now it's one integral. Now it's one integral. And there's actually no square roots anymore. So this is actually way easier. So antiderivative, this will be negative y squared plus 3y minus a third y cubed, 0 to 1. Again, the 0 bound doesn't do anything. That's all 0. Plug in 1, we get negative 1 plus 3 minus a third, which is 2 minus a third, 5/3, I believe. Hopefully that's right. Is that what we got last time? It is. It is what we got last time. Look at that, right? So it's another way to view integrals. And you want to think about, again, you want to think about whatever functions you're looking at, whatever region you're looking at, you want to look at vertical strips versus horizontal strips. So again, recapping here. I look at vertical strips for this region first, right? Because I think we intuitively, because we have so much more practice integrating with respect to x, we can just do it easier for some reason. But if you notice, the top function changes, okay? The top function changes once, which means I'll have two integrals, right? My starting integral, and then the one change adds another integral. So two integrals, I mean, we could do it. I mean, we did do it, but two integrals is more work than maybe I want to do. So now let's try horizontal strips. And now since the right and left functions don't change at all, they don't change, I only have to do one integral. Okay. I do have to reframe everything in terms of y, right? But that didn't take that long, right? In general, doing less integrals is easier and you're less likely to make mistakes. Okay. Awesome. Okay, that's that. Um, so let me give you guys one more here just to leave you off with, and then that'll be the end of class today. End of the video, excuse me. Um, Give me 1 second. Okay, go ahead and try this problem. This will be the last one we do today. I really want you guys to try practicing it. And yeah, so graph the function and now try to figure out, do you want to integrate with respect to x or with respect to y? Okay, so pause the video here. All right, if you chose to integrate with respect to y, that is the right choice, okay? So, what do I mean by that? Well, let's draw the picture and see what happens. So, square root x is going to look like this. X minus 1 down here. Y-intercept -1, slope of 1. So it's going to come up and then go like that. And of course, it goes down as well. Okay, and it hits 1 here. And then that intersection point, we don't know what that is yet. Okay, but just looking at the picture, this is our region here. So it's the only region bound by all three functions. And then you want to look at your strips. So if I look at a vertical strip, okay, so I'm moving along here, moving along. My top function and bottom function are staying the same, okay. Then I hit here and my bottom function changed. Okay, it changed once, which means I'll need another integral, so two in total, and then it doesn't change for the rest of it. So if we do with respect to x, we'll need two integrals. Now, if we look at horizontal strips, the right and left functions stay the same the whole time, which means I only need one integral. Now, I do have to change everything to be in terms of y, but that doesn't take too long. Okay, so I have y equals root x. Okay, I can switch that to be x equals y squared. Okay, just squaring both sides. Then I have y equals x minus 1. So I just add 1 to both sides. Or x equals y plus 1. Now those are in terms of y. These are y functions. So this is y squared here. This is y plus 1. And of course, this is y equals 0. Um, okay. Now I need my intersection point, right? I know my small bound is going to be 0. My upper bound right here, I don't know what y value that is. Well, we can get it very easily by setting the two functions equal. Okay, y squared minus y minus 1 equals 0. Now, unfortunately, this is not a nice value. We do have to do quadratic formula here. So we'll just have y equals negative b, so 1 plus minus square root, negative 1 squared minus 4ac over 2a. So this is 1, and then we're going to use the plus because the minus would give us a negative answer, but clearly that's a positive y value, so we use the plus, and then root 5 over 2. That's a very famous number, by the way. But yeah, so 1 plus root 5 over 2, that's our upper bound. And now we have everything we need. So our area is going to be 0 to 1 plus root 5 over 2, and then it's going to be the right function minus the left function, dy. Okay, and then antiderivative, 1/2 y squared plus y minus 1/3 y cubed, bounds. Okay, and then this upper bound is a little gnarly, so I'm just gonna leave it like this. Um, when we are doing integrals, I'm not gonna give you super crazy numbers like this. Um, yeah, and the zero bound gives us 0, so we can just ignore that. Okay. Okay, and this is about 1.515. Okay, that's our area. Okay. Again, here the bound was a little annoying. The one quadratic formula and stuff like that, but the concept of constructing the integral is really what I cared about, right? Picking, do you want to integrate with respect to x or y? And then once you get that, changing everything in terms of y. Okay. I really cared about that for this example. Okay. All right, that's the last new content of the term. Have a good day, everybody.